Hello, student. We'll continue discuss the magnetic field, and we started last lecture to learning some basic steps for the magnetic field and how to draw the direction of magnetic field. And today we try to cover some chapters as listed in this slides, and we try to start where we stopped last time, and we end up after we find the direction of magnetic field. We mentioned about the magnetic field can be generated using the current through the wires. So basically, we're gonna start to find the magnetic field through the current. So in that case, we have a wires, and that a wire is has a certain current with the directions, and I want to identify the direction of magnetic field. Since theoretically just the electric or particle of the charges moving around, so they create a magnetic field around that case. So here regarding for the wires, we have two notations you need to consider. How you find the direction of the current. It is comes in or comes out. And then we're gonna talking about the right-hand rules. With this, we're gonna use it often in this chapters to identify the direction of the magnetic field due to the current. So the directions for the current, if it is across that into the page. So imagine your current comes inside the page, it's just arrow. So when the current comes inside the page, we just see the X at the back of the arrow. So the X indicated the current comes to the page. And for the dot, that means that I use just see the head of the arrow would just as look at the point. So the dot indicated the current comes out perpendicular to the page, and the X comes into the page. And that's how to identify current into the page and out the page. And regarding for the right-hand rules, which is very basic one, you just hand your hand right, and your thumb will be indicated to the direction of the current, and your curl fingers show you the direction of magnetic field. It's very easy rule to use. So now, according for this rule or right-hand rules, if I put my hand rules in that wires here, and my thumb will be point up, in that case here, I end up with the direction of here's the current, direction of magnetic field point out in the left side, which supposed to be here is the just point. Here is the point for the magnetic field. And in another side, here's you curl your hand, and in the right side will be comes in the direction of the magnetic field as crosses. So that direction of magnetic field. Pass it in the current or right-hand rules. So let's use this notation to identify the current or magnetic field or the current directions using that rules. So let's go to the first examples here in the left side here. We have the wires, it has a current, and we don't know what the directions, but we are given the direction of magnetic field. So the magnetic field, this point out, and this is point in. Okay. So we need to identify what direction of the current. So we have to use our right-hand rules to identicate or to find magnetic and the current direction. Since I have magnetic field, I need my fingers point out in the right side of the wire. So if I apply the right rules, I found that when I point my right hand down, that's fit my situation where my dot here indicated to the current comes out and X comes in. So in that case, basically the current go in this direction. Here is the current. I look at another example here when we have the campus, and we mentioned last time to find the direction of magnetic field based in the campus. So in this case, the magnetic field, that's the direction of magnetic field. So we know the directions. And based on that, we need to find our current. Where is the direction of the current in that case? Based in the magnetic field direction. But again, we're gonna use the right hand situations where to try to find my curved fingers point in that direction clockwise. Yeah. So if I try to find out what the right hand, I will find out my right hand with the direction of the campus that when the current is pointed to the base. So the direction of the current just X toward the base. So in this perspective regarding for the dot and X, or the comes in and comes out. So here comes out. So here is represented as magnetic field as a dot. And another side comes in, so represented as X. Just to imagine what we are talking about for the direction of magnetic field comes in and comes out in 3 dimensions. And the thing that the reason why you use the right hand rules, because it is easy tool to use without a 3-dimension representation. So I can find the direction of magnetic field and the current without draw my direction or my vectors in the 3-dimension space. So here is a couple of other examples here. So you're asking to find the direction of the current or the direction of the magnetic field. We're gonna just more practice for the right hand. So you can pause this video and thinking how the direction of every single one of those 4 problems. So now let's do it together. So in the first case here, we have the current, and the current here is dot. That means it comes out to the page, and I will use my right hand rules. I will find my magnetic field directions in these directions using the magnetic or using the right hand rules. In the second example, we have the current here pointed to the left side. So I use the right hand with the thumb point to the current. Then I can write down what the magnetic field direction. So those here is my fingers, my curved fingers pointed out. That means here is the direction of magnetic field. Here is the dot in that case. And the top of the wires, that's where is the X are. So that's the direction of my magnetic field based in that kind. Similarly, for this case here, we have the current point out down the wire. So I try to fit my right hand by looking for my thumbs to indicate the direction of the current. Then my thumb or curl fingers pointed to the direction of magnetic field. So in this case, it's gonna be this directions here. And down of the wire is the magnetic field comes in. Last example here, we are given the magnetic field where is the down of the wires, the magnet or the current comes out, or the magnetic comes out, and the left side, the magnetic field comes inside the page. So according for the left hand, I wanted to fit my curl fingers where my fingers or curl finger pointed to the magnetic field comes out, and the left side and the down of the wires, and on the up of the wires point X, and I'm looking for my thumb directions. Where is the direction of my current? So in this case, this direction of the current. Now, regarding for what we have mentioned, the right hand rules, it is used to identify the magnetic field directions. Regarding how to find what the magnitude of the magnetic field, we have certain form, and that form it is based in certain distance from the wire or from the current. So the form is stated that is P equal mu 0, I divided by 2 by R. Where is the R? The distance from the wires. Okay. And it is logically, it's proportional to the current. So more current will be more magnetic field. And the mu here is that we call the vacuum permittivity with certain constant. You don't have to memorize it. And that constant 1.6 power to the minus 6. And the T here is the Tesla meter per ampere. As the unit for the magnetic field, it is Tesla. This is the new unit for us. So the Tesla, when you have the current by ampere and the radius by meters, P measured by Tesla. So this is the format to find the magnitude of magnetic field, and use the right hand to find the direction of magnetic field. The interesting thing for the Tesla here is some value, real value represent the magnetic field as the Tesla. And if you look at all those values, they are very small. So if you look at the superconducting magnetic, which is very huge magnetic field, it is no more than 10 Tesla. So all the Tesla as the unit, as a magnetic field, it's not, you're not expected to see that bigger numbers. That's when you make your calculation to find magnetic field. It doesn't make sense to find magnetic field. It is very huge number. So you cannot go more than 10, which something's very, very high magnetic field. So keep this one in your mind when you solve certain problem. And let's see, here's an example to how to find or how to calculate the magnetic field value. So here we have the magnetic field, and at the point P, here is the into the page. So the into the page, that means that current here, according for this one here, my right hand, so that my current directions, I don't know the directions, but let's see, according for that, and my right hand rules. The direction, I use my right hand. So that's what I expected, the direction of the current. But here they asked me to find the magnitude and the directions. So I find the directions for the magnitude. I will go and type my formula, P equal T, sorry, I have just to delete this one here. Just make sure you, T equal mu 0 times I divided by 2 pi multiplied by R. Where is the I? I know it is the I, it is 1 point. Oh, I don't have the I. You need to calculate the current. So here is the I wanted to identify. Mu, I have it. R, I have it. Here is the 2 centimeters. So which means 0.02 meters. And here is the P. We are given the P. It is 1.26 power to the minus 5, small value again, guys. And here is the mu, we have it 1.26 power to the minus 6 Tesla meter divided by A. So I have all those values. Just I can rub my equations again to find the current. Current in that case will be 2 by R times P divided by mu 0. I have mu 0, the same value as a Tesla. So I end up with the current, if my calculation is right, around 1.3 amps. And the directions to the left. That's the magnitude and the direction of my current. Okay. I'm gonna stop with that here, and the next video we're gonna continue to cover more topic regarding for the magnetic field.